welcome to the Geomistic channel. This lesson is part 3 of our series on area, where we'll be finding the area of any regular polygon. If you'd like a printable guided notes worksheet that follows along with this video, head down to the description and you'll find those links. Since we'll be finding areas of regular polygons, don't forget that a regular polygon is a polygon where all the sides are congruent and all the angles are congruent. So we're talking equilateral triangles, squares, pentagons, hexagons, etc. Now obviously we can't go through an example of every single type of these, but the good news is we don't have to, because the formula for any regular polygon to find the area is the same. Now, first some definitions. Now in a regular polygon, there are two line segments that we're going to be using here that are important. So one of these definitions is a term that you've heard with circles. You probably haven't heard it with a regular polygon or any polygon, but this is called a radius. Now a radius is the distance from the center of the polygon to any vertex. So in any regular polygon, you have the same number of radii as you do sides or vertices. So I could draw, in this case I have a regular hexagon, I could draw 6 radii all the way around. This hexagon. Okay, so this is called a radius. And you can think of this as if I circumscribed a circle around this regular hexagon. This radius would go to the edge of that circle. Now the second line segment that we're going to be looking at, probably a new word here, we're going to draw a line from the center of the hexagon to one of the sides, perpendicular to that side. Okay, so this line segment right here is going to go to the midpoint of that segment. It's going to bisect that central angle here. Okay, this line segment is called an apothem or an apothem. Okay, so this line segment is the perpendicular distance from the center of the regular polygon to any side. Once again, there's going to be 6 of those to each of those sides. So radius, distance from the center to a vertex, and the apothem is the distance from the center perpendicular to a side. Now there's a couple things that we're going to need to be able to do to find the area of any regular polygon. Now the central angle, we talked about that just a second ago. Okay, the central angle around the center of the circle, in this case you have 6 of them because we have a hexagon, but if I wanted to find the measure of these central angles for any regular polygon, because all these central angles are the same, all I would have to do to find the measure of each of those central angles is take 360, think we're going all the way around the center of that polygon, divided by the number of central angles that you have. Okay, usually they call that the number of sides, or n. So the central angle measure is just 360 divided by the number of sides. Next you'll have to have some experience in finding missing sides of right triangles. So we might be utilizing some of our right triangle rules like the 30-60-90 or 45-45-90 rules. And we'll also be using some trigonometric ratios, sine, cosine, and tangent, to find some missing pieces as well. Now the reason we'll need these is because the formula that we're going to be using is really all about these triangles that we've created with this radius and the apothem. So what we're going to do is we're going to find the area of one of these triangles. We'll just go with this one down here. And since all of these triangles are congruent, if I can find the area of one of them, I can just multiply that answer by the number of triangles, and that gets the area of the whole figure. So, knowing that my triangle formula to find the area is 1/2 base times height. Okay, so to find the area of any triangle, it's just 1/2 base times height. If I look at this bottom triangle right here, think about what I have. Okay, the length of the base is just the length of one of the sides of the regular polygon. So this is just the length of a side. I'm going to call that, we'll just call that S for side. And then the height of this triangle right here, that is the apothem. Okay, so that value right there, the height of that triangle is the apothem. So if I take my formula for the area of a triangle and replace it with what I have in my situation here, the area is just 1/2 the base, which is just the side length, times the height of the triangle, which is just the apothem. Okay, so I've got 1/2 of the side length times the apothem. So if I have that area, the area of that entire triangle, and I know that there are, in this case, 6 of them, but n of them, the number of sides, tells you how many triangles you have, I would take this whole thing multiplied by the number of sides, which would get me the area of the whole figure. Now, one last simplification here is to recognize that if I took a side length times the number of sides, that's really just the perimeter of this figure. So side length times number of sides is perimeter. So if I simplify this a little bit, because multiplication is commutative, I can kind of do them in whichever order I want. I'm going to multiply the side length by the number of sides and call that perimeter, which is where we get our final formula. 1/2 apothem, and then side length times number of sides is the perimeter. Okay, so we've just developed the formula to find the area of any regular polygon. 2 things I need are the apothem, that value that goes from the center to one side perpendicularly, and the perimeter, the length or the distance all the way around the figure. Now, just like with any formula, if you know those 2 values, it becomes really simple. You're just multiplying 1/2 times apothem times perimeter. You just multiply them all together. Where it gets a little tricky is when you're missing some values, or if you have certain values inside the regular polygon, but maybe you're missing one of the 2. Maybe you don't know the apothem. Let's do some examples. Let's start with a pentagon. Okay, so let's say that's a regular pentagon. I want to find the area of this thing, and I know that one side is 6 inches. Okay, so that's all I'm given. So one side is 6 inches. I want to find the area of that regular pentagon. My formula, area is equal to 1/2 of the apothem times the perimeter. I always start here just because it's helpful to kind of map out what we're doing if we know what we need, and then kind of look at our figure and decide, what do I have? What am I missing? So in this picture, do I know the apothem? Not directly, it doesn't show me that. Do I know the perimeter? Well, if I know one side, and since all the sides are the same in a regular polygon, I can just multiply that side by the number of sides. That gives me the perimeter. So if there's 5 sides and each side is length 6 inches, 5 times 6, that gives me the perimeter, and that's 30. So I'm going to go ahead and start building my formula here. 1/2 apothem, I'm going to leave that blank for a second because I don't know what that is. And then the perimeter is 30 inches. All right, so 1/2 apothem times perimeter, which is 30. Okay, so at this point, now I have to decide how I'm going to find the length of this apothem. So again, the apothem, center to a side, perpendicular to that side. Okay, and the strategy here is we're going to utilize those triangles at the bottom. So remember at the beginning, if I draw a radius to each vertex, you start creating triangles. And I can do that all the way around to get 5 of them, but this is really the one that I'm worried about here. This is the one that I'm after. So in this triangle, I'm trying to find the apothem. I'm going to start building up the information that I have in this figure. So what else do I know in this triangle? What other values do I have? Well, I know that all the sides are 6. So across the bottom here, I know that this whole distance is 6, split by the apothem into 2 pieces. So I'm going to go ahead and call that 3 and 3. So 3, 3, the whole base is going to be 6. The next thing I can do is I can figure out the measure of this central angle right here. Okay, so how did we do that again? If I take 360 divided by the number of central angles, so again from red line to red line for each radius, these are all equal. So I can take 360 divided by 5. 360 divided by 5 will tell me what the measure of that central angle would be. So if I take 360 divided by 5, That gives you 72 degrees. So this central angle right here is 72 degrees. Now what I like to do, sometimes it gets kind of messy when you're dealing with this little triangle inside. Kind of just go to the side, just draw that triangle. So radius, radius. Make it a little nicer here. So you got the radius on either side. Got the base. You got the apothem. Okay, so if a 72 degree angle is right up here, this central angle, so this central angle up here is 72, because that apothem bisects that angle, cuts it right in half, half of 72 is 36. Okay, so we got 36 degree angles up there, 3 and 3, apothem is what's missing. Okay, so really this becomes as a triangle problem. If I have a right triangle, okay, so I'm only gonna look at half of this now. If I have a right triangle where I know an angle, and I know one side, I'm looking for another side, what strategies can I use to find that missing side? Well, it's not a special right triangle, it's not a 30, 60, 90, I've got a 36 degree angle instead of 30 degree angle, but I can utilize sine, cosine, tangent. Okay, I can use my trig functions to figure this one out. And that's what I'm gonna do here. So if I look at what I have, I've got a 36 degree angle. Opposite of that 36 degree angle is that side of 3, so I'll put a little O right there. Nothing on the hypotenuse. The adjacent leg is that apothem, so this is the adjacent leg. Here's the hypotenuse. I've got opposite leg and adjacent leg. Okay, opposite leg and adjacent leg. If you remember your rules, what your ratios are, if you don't remember, utilize this little mnemonic, so katoa. If you have the opposite and you're looking for adjacent, O and A, it's right there. So this is going to be a little tangent problem. I can write it out as tangent, then my angle, 36 degrees, equals the opposite leg, which is 3, over the adjacent leg, which is my missing apothem. I'm going to put that tan 36 over 1 to create my proportion, and then go ahead and take the cross product. So 3 times 1 is 3. A times tan 36 is just A times tan 36. And then last step, to solve for A, I'm going to divide both sides by tangent 36. So tan 36 over tan 36 is 1. 3 divided by tan 36 is what I'm looking for. So I'll find my calculator here. Make sure I'm on. So I've got 3 divided by tangent of 36 degrees. And it looks like we got about 4.13. Okay, so my apothem there is 4.13. Okay, so that's that distance right there. Looking at my picture, this side is 3, that's a shorter leg, the longer leg, 4.13, looks like that makes sense. And I'm going to put that right here, 4.13. Okay, so with that tangent problem, I have completed my formula, 1/2 times 4.13 times 30. Go ahead and type that in. So I've got, I'll just do it this way, 4.13 times 30, and then half of that, or I'm going to just divide that by 2. Oops, one too many. Looks like I got 61.95. Accidentally hit equals twice. So 61.95 is our area. And since it is an area, we've got our label. This is in inches. So we're going to go with square inches for our area here. Okay, so you can see there's a little bit of a process. Again, if you're missing a portion of your formula, you kind of have secondary problems to find those missing pieces. One way is to use sine, cosine, and tangent. Okay, let's do another. Let's go back to the hexagon. All Alright, so in this case, got a regular hexagon. This time I'm going to give you a radius length. Okay, so a radius length of 2 centimeters, and I want to find the area of this regular hexagon. So again, I'm going to start with my formula and then decide what, if anything, do I have. So do I have the apothem here? Nope, not yet. So it's right here. That is the apothem. Don't have it yet. Do I have the perimeter? Unfortunately, no, I don't have the perimeter either. So I don't have the length of any of the sides, I just have a radius. So I'm missing both parts here. Okay, so what do we have to do? Once again, start with that triangle down there at the bottom. So I'm gonna go ahead and draw another radius. This triangle is what I'm gonna deal with. I'm gonna draw it a little bit bigger right here so you can see what we're doing. There's the base, there's the apothem. Okay, so my 2 centimeter radius, apothem here, I don't know what it is, side length, I don't know what it is, so I gotta find 2 things in this case. Now, the first place that we can find missing pieces again is that central angle. So again, I've got 6 radii all the way around. Around that center point, I would have 6 central angles. So I'm gonna take just a quick 360 divided by 6, and that tells you that that central angle there is gonna be a 60-degree angle. Okay, that's 60 up here. So this whole thing right there is 60, split in half, we got 30 and 30. Now the good news here is that because that's a 30-degree angle, what we've created is one of our special right triangles. This is a 30, 60, 90 right triangle. So knowing those 30, 60, 90 rules in this case is going to be really helpful. Those rules, if you don't remember, in a 30, 60, 90, is that your short leg doubled gets you to your hypotenuse, and then the short leg times the square root of 3 gets the long leg. Okay, so those are those special right triangle rules. If you don't remember those rules, video right up there, you can go back and check that one. That will show you what those rules are and how to use them. So what I have again is a right triangle, 30, 60, 90. I have the hypotenuse, and I really need both the short leg and the long leg. Short leg is going to be able to get me to the perimeter. The long leg is that apothem. So to get from the hypotenuse back to the short leg, if the hypotenuse is just double the short leg, I would just divide by 2 or take half to get to that short leg. So if this is 2, half of 2 is just 1. And then to get to the long leg, take that short leg and multiply it by the square root of 3. And what is 1 times the square root of 3? It's just the square root of 3. And with that information, I can get my apothem and my perimeter. Apothem I already have, it's the square root of 3. So building up my formula here, apothem is the square root of 3. And then the perimeter, if I've got this short leg is 1, the other short leg over here on the other side, the other triangle is 1, which makes the entire base 2. Now a quick shortcut, when you're dealing with hexagons, recognize that this triangle that you've created down here, it is an equilateral triangle. Because this is 60 up here, 60 degrees, and this is 60 degrees, and this is 60 degrees, that is an equilateral triangle. So your radius of 2 really is also this base of 2. All 3 of those sides are going to be 2. So quick shortcut, if you can remember it, if radius is 2, your whole base is 2. That's only for a hexagon. That's only because that's equilateral. Now, if the base is 2, because I'm looking for perimeter, I've got 6 sides, so 2 times 6, that gives us a perimeter of 12. And now I've got my formula. Here I'm going to leave my answer in simplest radical form. You could get a decimal here if you wanted to go ahead and type that into your calculator. That's up to you. Just look at your instructions and see how it asks you to write your answer. So I've got half times 12 root 3 times 12. Half of 12 is 6. And just leave my 6 root 3 as my answer. We are in centimeters. So I've got 6 root 3 centimeters squared. That is my area. All right, let's try another. So again, this formula 1/2 AP, this works for any regular polygon, which includes squares. And there's lots of different ways to find areas of squares. The one we're going to do right now might not even be the most efficient way. But just to show you that it does work for any regular polygon, let's go ahead and do this. So say you have a square with a radius of 8. We'll go with meters. Square with a radius of 8 meters. Now if you remember your formula for the area of a rhombus, that might be the quicker way to do this one, but we're going to use 1/2 AP just because that's what this lesson is about. 1/2 AP. Okay, now once again with the radius, I don't have the apothem or the perimeter. But as always, I'm going to start by just utilizing this triangle. So I'm just going to blow it up down here, make it a little bit bigger. We'll say this is 8 meters. Apothem down the middle is right here. And next step is to find the measure of that central angle. So again, you got the radii all the way around. In this case, we've got 360 divided by 4. 360 divided by 4 is 90, so I've got a 90-degree angle up top. Apothem splits it down the middle, and we're dealing with 45. And since that's 45, we got 90 here, this is going to be 45. We've got a 45, 45, 90. Now again, 45, 45, 90, it's a special right triangle, the rules of which look like this. Legs are the same. Leg times the square root of 2 gets you to the hypotenuse. Okay, so there's your rule. Again, check back the video on 45, 45, 90s if you don't remember those rules. Okay, so we got a 45, 45, 90 with a hypotenuse. I need to know the legs, which are the same. Okay, the legs are congruent. But if I have the hypotenuse getting back to the leg, if I multiply by root 2 to get to the hypotenuse, I'm going to divide by root 2 to get back to that leg. So if this is 8, 8 divided by root 2 gets me those 2 legs. So 8 over root 2. Now you could rationalize the denominators here. I'm just going to leave them as is for now, just because when we put them into the formula, it's going to kind of clean up a little bit. So I'm just going to leave them like that, 8 over root 2. Okay, so 1/2 apothem times perimeter. Apothem, we got 8 over root 2. And then perimeter, if I've got 8 over root 2 for this piece is also 8 over root 2. So the whole thing is going to be 16 over root 2. And since one side's 16 over root 2, all 4 sides are 16 over root 2. So if I take 16 over root 2 times 4 to get the perimeter, that's going to be 16 times 4, it's 64. So I've got 64 over root 2 would be the perimeter all the way around. Okay, so we've got our formula. Looks kind of messy, but things will work out real nicely here. If I go ahead and multiply, we'll go ahead and multiply 64 by 8. So let's deal with the half at the end here. 64 times 8, that's 512. And then root 2 times root 2 is root 4, and the square root of 4 is just 2. So you can see that those cancel, or don't cancel, but they multiply, that gets rid of the root. Okay, so 512 over 2 times a half. 2 times 2 is 4. 512 divided by 4, that is 128. And we are in meters. So we got the area of this square, 128 square meters. All right, let's do one last example. Okay, let's go with the equilateral triangle. Okay, so we've got an equilateral triangle. I will give you one side length of 10. Okay, so to find the area of this equilateral triangle, I've got one side length of 10. Now, a triangle, of course, is just half base times height. I've got a base, but I don't have a height. One option is to use this figure to find the height. Again, I'm going to go with 1/2 AP, use our formula to show you that it does work, regardless of any shape, as long as it's regular. So if I'm using the formula here, I need the apothem, so there's the center of that regular triangle or equilateral triangle. Go ahead and draw a radius around there, like so. Okay, Good news is we already have the perimeter. Since we have a side, all the sides are going to be 10. So 10 times 3 is 30. So let's start there. So I got 1/2 apothem times perimeter, where the perimeter is 30. So all I need here now is the apothem. I'm trying to find that value right there. So if I draw this bottom triangle here just a little bit bigger, what I want to do first is I want to find that central angle up there at the top. To do so, I'm going to take 360 divided by the number of central angles, which is 1, 2, 3. So 360 divided by 3 is going to get us a central angle of 120 degrees. So this whole angle is 120, again split in half by that apothem. 120 divided by 2 is 60. So once again, I've got a 30, 60, 90. The whole base is 10, so cut in half, I've got 5 and 5. I've got my short leg is my apothem, my long leg is 5. I want the apothem, so I'm going from the long leg back to the short leg. If you remember your rules again, long leg back to short leg is divided by the square root of 3. So my apothem here is 5 over root 3. Once again, you can rationalize if you want. I'm just going to leave it as 5 over root 3. Because I think on this one I'm just going to get a decimal. I'm just going to go ahead and multiply it all together. Okay, so I got what I need. I'm just going to go to my calculator here. I'm just going to multiply all that stuff in here. So let's go half, use 0.5 for half, times, we'll go 5 over the square root of 3 times 30. So depending on your calculator, you might have to kind of do it one piece at a time. Graphing calculators, usually you can just type it all in at once. As long as you get all your parentheses in the right way, you should be fine. So we've got 43.3. And no label this time, I didn't give you one, so we'll say units squared. Don't forget that label. 43.3 units squared for the area of that one. All right, so there is the area for any regular polygon. With all formulas, again, if you have what you need, it's real easy, you just plug it in. When you're missing things, that's where it gets a little bit trickier. Just utilize those triangles. All of your triangle rules are going to help, whether it's 30, 60, 90, 45, 45, 90, your trig ratios, sine, cosine, or tangent, all those are in play. Alrighty, if this was helpful for you, please leave a like and consider subscribing to the Geomastic channel if you would like to see more videos like this one. Thanks for watching. We will see you next time.